Forces with the same point of application are called concurrent forces. If all forces are on a two-dimensional plane, they are called coplanar forces. Since we assume a rigid body, the forces can be shifted along the line of action, so they are called sliding vectors. If we now have two different forces, here in the example F1 and F2, we can add these forces to a resulting force R. For this, we use the parallelogram of forces. Here we create a parallelogram with the two forces. The diagonal then represents the resulting force R. Another possibility is the force triangle. Here the force F1 is drawn. The force F2 is attached to its end. The line from the origin of F1 to the end of F2 now represents the resultant R. We can also apply this principle to a system with any number of forces. In this example, we have 6 forces, F1 to F6. Now we draw F1, hang F2 on it, then F3 to F6. The line from the origin of R to the end of F6 is now the resulting force R. To illustrate the principle of the rigid body and the sliding vectors, I have now shifted the forces on the body a little. Remember, the forces can be shifted along the line of action on a rigid body. Also, with the force polygon, the order F1 plus F2 plus F3 to F6 does not have to be followed. This can also be changed at will. At the end, the same resulting force R is always determined. If we only have one force, here the resulting R from the example above, we can decompose it into two forces on two lines of action. If there are only two lines of action on a two-dimensional plane, there is only one solution for the decomposition. This can be determined with the help of the force triangle. If, on the other hand, three lines of action are present in three-dimensional space, there is no clear solution. The number of possible decompositions is infinite. If we want to add two forces, we can also use their components. Here in the example, we have two forces, which we decompose into the x and y components of the Cartesian coordinate system. We can now determine the resulting force by adding the components. If we now look at the components of the resultant, the x component of the resultant results as Rx equals F1x plus F2x, and Ry equals F1y plus F2y. Now we assume a system in which 6 different forces act. We want to determine the resulting force. For this purpose, we first calculate the x component of the resultant force. This can be written down as Rx equals F1x plus F2x plus F3x plus F4x plus F5x plus F6x. To abbreviate the whole thing, there is the sum sign, which is represented by the large Greek letter sigma. Below the summation sign is the start index I. In this example, the index starts with 1. Above the summation sign is the end of the sum, n. Here in the example it is 6. After the summation sign comes the formula in which the index I is always increased by 1 from the starting point to the end. So the sum sign means the same as described in the equation above, namely f1x plus f2x plus f3x plus f4x plus f5x plus f6x. This can be generalized even further, and the end can simply be indicated by n. This is now the sum, which starts at f1x and adds up all forces until the force fnx. The n stands for the end of the respective system, where the sum formula is used. In statics, we always use the sum formula when we sum over the components of a force. The I below and the N above can also be omitted. So Rx is the sum of Fix and Ry is the sum of Fiy. We have already discussed the balance of power in the previous lesson. In statics, the forces add up to 0. The resulting force is 0. Here in the example, a body is loaded by 4 forces. If we now set up the force polygon of these 4 forces, we see that there is no resulting force, or the resulting force is 0. Thus, we can derive the two conditions of equilibrium. The sum of all forces in x direction is 0, and the sum of all forces in y direction is 0. If we have a connecting element which is much longer than its cross-sectional area and can only transport tensile forces along its axis, this element is also called cable or rope. The dead weight is neglected when considering the tensile forces. Due to the elasticity of the rope, these are often passed over pulleys. Here in the example, you can see a rope which is led through 2 pulleys. The structural element, which like the rope is much longer than its cross-sectional area, but unlike the rope can also transmit pressure forces, is called bar or rod. Now we consider the contact force between 2 bodies. As we know, in statics we consider rigid bodies. This means that the bodies touch each other at an infinitesimal small point. At this point, the contact force acts with the same magnitude but in opposite directions on both bodies. The contact force can be divided into 2 components. The tangential force lies on the contact plane and the normal force is perpendicular to it. The normal force is based on the pressure between the 2 bodies. The tangential force is based on the roughness of the bodies. If the bodies are ideally smooth without roughness, the tangential force is 0.